Hi, for our project, we chose to do something with OpenVLC. Our presentation is split into 3 parts. First, what is OpenVLC? 2, what is our project? And finally, what did we get done? OpenVLC is an open-source, flexible, and low-cost visible light communication system platform. Sometimes also referred to as Li-Fi. Visible light communication uses the off-the-shelf visible light LEDs to transmit data using the visible light spectrum. OpenVLC's mission is to help progress the research and industry in visible light communication systems by making the technology easier to access, for example, get into the hands of students like us. Li-Fi is envisioned to be the next big thing in wireless communications. Functionally, the system would work like this. You would have 2 computers with capabilities to both send and receive data. You would also have a lamp that would flicker to output data to the other computer. Then a sensor would read the flickering and convert it back into readable data for the computer receiving the data. With Li-Fi, we can efficiently use our existing light infrastructures to provide high-speed, secure wireless communication. Li-Fi does not interfere with radio frequencies, which means you can use it in hospitals, power plants, petrochemical plants, and airplanes. The illumination area of Li-Fi is confined to the area that the light touches, which means unlike Wi-Fi, your signal remains hidden to anyone outside this area. The light is controllable. Simply shut the door or pull the blinds to protect your network from prying eyes. These features and capabilities sound great, but this is where we could go. Here are some of OpenVLC's current capabilities. Throughput is 400 kilobits per second. Transceiver distance can be up to 4 meters. The drivers and demos are written in C. OpenVLC targets applications for IoTs, and OpenVLC is used in more than 20 research groups.
Hopefully now you have a good idea of what OpenVLC tries to bring. Now, what is our project? We were approved one of the Honeywell projects just before needing to turn in our methodology assignment. But due to complexities, we were requested this project be halted the day before our technical reporting assignment was due. And we had to pivot greatly and accept this task. By the end of this semester, fabricate an OpenVLC PCB, install and set up all associated software, and run the provided demos. Next semester, our task is to establish simplex communication and transmit custom data. As an optional stretch goal, we would have the devices talk to each other, as in instead of having a dedicated transmit station and a dedicated receive station, have the roles switch after each task. This is half duplex. So, how are we going to accomplish this semester's task? We have been provided the resources we need: the schematics for our transmitter and receiver, the list of components, Gerber files to print the PCB, a place to print the PCB, instructions on how to set up the BBB board our PCB will connect to and run our demos, finally a place that has all available references to OpenVLC.
Which brings us to, what did we get done? We were able to order all of our components, but some components are still in transit. One really important component will not arrive until the second week of January. We were able to get the OpenVLC PCB ordered for printing. When the PCBs arrived, we did some initial continuity tests on the PCB to verify each pad is connected to the correct traces. We were able to solder on every component except for our lamp for our transmitter, and obviously the part that is still in transit. Our ADC for the receiver circuit is not soldered onto the PCB. Keep in mind that these components are extremely small to minimize troubleshooting. As each component was added, we verified its connection with the surrounding pads and referenced the schematics to make sure it was truly connected to their neighbors. This validation added 30 minutes to 2 hours with working on each component. With about 42 components and 2.5 weeks of work time, a good 50 hours was spent fabricating this OpenVLC PCB. Next, how did we test what we have built so far? We tested our PCB by measuring the voltage at where the lamp would be. We injected a 3.3 volt high on our 2 input pins, and the voltage at the lamp measured the following. During the tests on our last slide, our PCB wasn't on top of our SBC because after setting up our SBC, we learned that we have a software issue. Our outputs from the SBC were stuck at a low and high, so we weren't able to capture the square wave output we were expecting. Pictured here are our first attempts to dial in the oscilloscope. So, to recap, what did we get done? We ordered and received 97% of our components. We soldered and verified 95% of a single PCB. We needed to fabricate 2 PCBs. At the moment, we have 1, and we'll have the second fabricated in the next 2 weeks. Our SBC has all of the required software installed, but we need to troubleshoot the drivers to see why our outputs are not changing. And finally, the demos are ready to be run, but we need to dig into the driver source code to figure out what's wrong. Here is our Gantt chart. And here is our budget.